how to pick the best looking hypothesis.
Okay, so here's the basic idea we're going to try to implement. So, step one, pick a random hypothesis. For example, this one. Okay. Pick a random hypothesis.
A random hypothesis.
Okay. And, you know, I'm going to envision that the first step doesn't work. So we're going to have to somehow update it. We're going to have to change it so that it gets better. Okay, so let's call the hypothesis that you pick at step one W of 0.
Okay, so W of 0.
Of 0, I'm preempting the fact that, you know, we're going to have iterations, okay, and we're going to gradually improve this hypothesis. Okay, and that's the basic idea. And so we're currently at iteration 0. Okay, and when you've picked a hypothesis randomly, it's typically going to look something like this. It's not going to work. It's not going to look good. Okay.
It's not going to look good. So step 2.
Okay. So what do you do if it doesn't look good? What do you do if it does look good? So if by chance you happen to pick the hypothesis, which is the line that's going down here and gets everything correct, you're done. Okay. So we only need to address the situation where the hypothesis you picked does not look good.
Step 2. The hypothesis does not look good.
Okay. So that's the only situation where you need to worry about step 2. Okay. In which case, there's at least one data point on which the hypothesis does not look good. Okay. In this case, for example, there are 2. There's this red X and this blue 0. Okay. Because the hypothesis is saying blue for this red X, and it's saying red for this blue O. So, pick
any data point that does not look good.
Okay, so, for example, this red X. Okay. Because we're in a situation where the hypothesis does not look good. And move the hypothesis in the direction that tries to make this look good. Okay. So move the hypothesis in this direction. Okay. Now, why? Because by moving it in this direction, we're trying to make this guy look good. Okay.
Move hypothesis to try to improve that bad point.
So, how? And what can go wrong? So let me just mention what can go wrong. What can go wrong is when we move this guy up in order to improve this, maybe we end up here. Okay, but now look at what has happened. We end up here, so everything above there is now blue, everything below here becomes red. So while we did improve this guy and make this guy classified correctly by that line, we've made the situation worse for this guy, and that guy has now become a red, but it's actually a blue 0, a blue O. Okay. So what can go wrong is in improving the situation for one data point, we might mess up other data points. Okay. We'll deal with that later. Okay. Because before we can even address that issue, we need to know how do we move the line up. Okay. So let's consider this situation. Okay. In this situation, okay, my weights, sine of W transpose X, so let's call this X star. So let's call the bad data point, let's call this X star. Okay. So in this case, the sine
of W0 dotted into X star
has got to be, is positive. Okay, the sign is positive, but the actual Y star, okay, is less than 0, okay, because it's disagreeing. So what we would like to do is we would like to get the sign of W0 dot into X star, we would like to get that to be negative. Okay. So let's look at the situation. So this W dot X star, so W0 dotted into X star is positive because its sign is positive. So what's the situation? The situation is like this. You've got X star and W0. Okay. And they're aligned so that their dot product is positive. Okay. What we would like to accomplish is we would like to get W0 to be something like this. Okay. Now they are misaligned and the dot product will be negative. Okay. But how do we get W0 to become something like this? Well, we have to add on to W0 this vector. But look, this vector is more or less the negative of this vector. So this is negative X star. So it suggests that we should add on to W0 the negative of X star. So W1, so we update W0 to W1, should equal, okay, W0 minus X star. Okay? So here we found a bad looking data point, and in order to move the hyperplane, in order to move the line or the hyperplane so that it correctly classifies this data point, we should, in some sense, we should be subtracting X star. Let's look at the other case, okay, which is this blue data point. Supposing we had decided to work with this blue data point, which is also looking bad. In that case, okay, so for this blue data point, for the blue data point, okay, well, the sign of W0 transpose X star must be negative, okay, because this blue data point is on the other side. Sign of W0 dotted into X star is less than 0. Okay, and we'd like to flip it. Okay, so let's look at the picture. So we have X star. Okay, and the dot product is negative. So this is W0. Okay. And we would like to move W so that the two vectors are more aligned, i.e. so that this dot product becomes positive. So we would like W0 to become something like that. Okay. Which means that we need to add to W0 this vector. But look, that vector is basically X star. So we should update W0 to W0 plus X star. So in this situation of a bad data point, W1 should equal W0 plus X star. Okay, so let me summarize. This was the situation when Y star was equal to -1. This was the situation when Y star was equal to +1. And notice that the updates are different. Okay? When Y star is -1, you update by subtracting the data point. When Y star is +1, you update by adding the data point. We can combine both of these into a single update, which is that W of 1 should equal W of 0 plus Y star X star. Because notice, Y star is -1, you have a minus here. Y star is +1, you have a plus here. That's exactly Y star. So minus when it's -1, plus when it's +1. So it's not that this update is any different from these, it's just that it's a compact way of representing this update. Okay. So how is addressed by the update rule. Okay. The update rule.
Okay. And now we can be a little more general. So the update rule is that, you know, what we can do is we can say we'll set t equals to 0 in step 1. And the update rule is that you update t, so t equals t plus 1. Okay, so at the first step t equals 0, so now at the second step t equals 1. Okay, and w of t, which would be w of 1, is equal to w of t minus 1, so whatever it was before, plus y star x star, where x star is the applicant data, so it's the input vector for any bad-looking data point. So we make the update. And now we can check. Do you have a good-looking hypothesis? If you have a good-looking hypothesis, you're done. If not, you just repeat. Repeat. Okay. So how to pick the best-looking hypothesis is a very simple algorithm. Well, this algorithm goes by a name. It's called the Perceptron learning algorithm, or the PLA. So, we have simultaneously specified what's the criterion to use in order to pick a hypothesis. We're going to use the hypothesis that looks good, the hypothesis that looks the best. Okay? And what's the algorithm that implements that picking? The perceptron learning algorithm. Okay. So, what can go wrong? What can go wrong? So, 1. Okay. The criterion is bad. In other words, just because it's a good-looking hypothesis, it doesn't necessarily mean that on the next data point that pops up, it's going to work. We'll deal with that question later. Postponed. Two. Okay. The algorithm that does the picking, is considering only one point at a time. So it improves the situation for one point. Okay, then it improves the situation for another point, and then it improves and improves and improves and improves. And in improving for one point, it might mess up a whole bunch of other points. Okay, improving for one point might mess up. In fact, it might mess up all the others. And the third thing that can go wrong is what happens if the data is not separable. So what happens if it is not possible to separate the blue zeros from the red x's? And that's nice. Okay. The red x's. Okay. And this is a serious condition that is not under our control. Okay, so we're saying what happens if it's not possible to separate the blue zeros from the red x's. Okay, so there's no way to construct a hyperplane such that on one side you have all the blue zeros and on the other side you have all the red x's. Okay, such data is called unseparable data. So what happens in this situation? So let's see what actually happens for the algorithm. The algorithm says, is your hypothesis looking good? If it's yes, you're done. If it's no, you do an update.
Okay. Now, for the new hypothesis, can it possibly be looking good? No, because the data is not separable. So it comes back, does the update. Okay. Is the new hypothesis looking good? No, so it comes back, does the update. This algorithm will never terminate. Infinite loop. Now, we have to deal with this for two reasons. One, we don't like creating algorithms that have infinite loops. And two, it's often the case, in fact, it's almost the norm, that data will not be separable. Okay. And it turns out that we'll deal with this later. There are many simple tricks that we can use to deal with this situation. One of them is called the pocket algorithm, which we will talk about later. Okay. So, postponed. Okay. And so let me just show you that we can deal with the situation where you improve for one point. It's possible that you might mess up all the other points. Okay. So let's consider the situation of separable data. So separable data. Okay. So we're postponing the unseparable data. We're postponing whether or not the criterion is bad or good. Okay. We're considering separable data and asking whether when you improve for one point, you can mess up all the other points. Okay. And so here's the miracle of the day. And it's a theorem. If the data is separable, then PLA finds a separator in finite time. So first of all, why do I say finds a separator? Because let's look at separable data. Okay, so separable data, you've got blue circles and you've got red X's. Okay, and you can separate. Okay, so you can find a line that separates blue from red, but if you can find one, you can find many. Okay, and so all we can expect of the algorithm is to find one of them. Okay, fine. Now, why is this a miracle? Okay, why this is a miracle is because up to now, probably in your computer science career or what have you, you develop algorithms like here's a list of numbers. There are 4 million numbers. Find me the minimum. Okay, so the important thing is here's a list of numbers and it has size 4 million and you can find the minimum. So it's a finite list. Okay? So all algorithms typically operate on a finite object, okay, like a finite list. And then, even if you're struggling to figure out what's the best way to solve the problem, there's always a brute force way. Okay? And what's the brute force way? For example, in a list, you try every element and see if it's the minimum. Try every element. Okay? So we could perform the same kind of algorithm for the perceptron hypothesis set. We could try every possible hypothesis and see is it a good-looking hypothesis. And that's going to fail miserably because the hypothesis set is infinite. Okay. So this perceptron learning algorithm must be doing something much more spectacular than trying every hypothesis. Okay. And that's what this theorem says, that as long as the data is separable, it's not going to bounce around forever. It's not going to bounce around forever. And so we have managed to find an algorithm that can find a unique guy that separates a very special hypothesis that separates blue from red from among infinitely many. Okay. That's a miracle that it can do that. So let me show you, an example of this theorem in action. So here's an example data set that I've constructed. It's very similar to the one we had on the board. Okay, so you have a bunch of customers with age and income who defaulted and a bunch of in red X's, and you have a bunch of customers who did not default in blue circles. Okay. And the algorithm starts with a random linear with a random linear separator. Let's even say it starts with 0 weights. So that separator which has 0 weights assigns a credit score of 0 to everyone. So such a credit score of 0 to everyone is going to get all the positive guys wrong. So let's pick one of the positive guys as my bad looking data point and move the hyperplane in that direction, and look what happens. It moves it so much to get this blue guy correct that it classifies everything as blue. Okay, so now there's a bad data point, the red X.
Okay, so let's pick this red X and implement the algorithm which moves the weights according to the formula. W is updated to what it was, W before plus Y times X. Okay, and so it now moves up, the linear separator moves up and certainly gets the red one we were focusing on correct, but now it's messed up this blue one, and also it still hasn't gotten these other red ones. So let's pick a bad looking data point, this red X in the blue region. Okay, update. Oh, now it's classifying everything as red. And so this is exactly what we talked about, which was the problem, that in trying to get one data point, so before at least 4 of the blues were looking good, but now in trying to get this red guy to look good, boom, we messed up all the blue guys. And the worry is that will this go on forever? So if we continue, it's almost correct and almost messes up more, and boom, now it's finally done. Okay. And that's the theorem at work. It says that you can keep bouncing around like this, but only a finite number of times. Eventually, you will find a separator. And the question then becomes, after how long? Well, you will answer that to some extent in the homework when you prove this theorem. And of course, we already mentioned what to do if the data is not separable. And here's an example of data that cannot be separated by a line. Okay. So, bottom line, which we already mentioned, is that from the computational perspective, we can search this infinite set. That's a miracle that we can search an infinite set. Okay. And we can find the hypothesis that looks good. Okay. But then, the question is that just because it looks good on the data doesn't mean that it is good. In other words, remember, we want to predict on a new data point. And we will discuss that issue at length. Trust me, we will discuss that issue at length.